Alright, so we assume that X is complete and pre-compact, and we want to show that X is a compact metric space. Well, how can you show that a metric space is compact? Well, you have to take any open cover and show that it has a finite subcover. If you cannot prove something directly, as usual, you just assume the the negation of that. So let's do that. So assume on the contrary that XD is not compact. Okay, so my aim is then to arrive at a contradiction. Okay, so let's start with this assumption that it is not compact. Hence, there is some open cover. Let's say O alpha, uh, so that uh, okay, so that this open cover has no finite subcover. In other words, finitely many of these open sets will never cover X. So we assume that. So we uh, have that. So for any, let's say alpha 1 up to alpha k, X cannot be a subset of O alpha 1 or alpha k. Okay, this has no finite subcover, means no matter how you choose finitely many of them, their number could be very large but always finite. Their union will never contain X. Okay, there will be always some points of X which lie outside this union. But on the other hand, we assume that this is complete uh, metric space and it is pre-compact. So I have to make use of those assumptions. How? The strategy is the following. We will form a convergent sequence first. And that will give me a contradiction. And to form the convergent sequence, I'll actually form a Cauchy sequence, and our metric space is complete. Therefore, that Cauchy sequence will be convergent. This is how we do it. Okay. Let epsilon equals 1. Okay. Since XD is pre-compact, X is covered by finitely many epsilon balls. X can be covered by finitely many balls of radius 1, which is epsilon. So I have this. This X lies inside a union like this. X1, let's say 1, X2 radius 1, and how many of them? Finitely many of them. Let's say K1, 1, for some X1 up to Xk1. Okay. But I know that, on the other hand, X cannot be covered by finitely many O alphas, right? X is never a subset of such a union? Well, this means what? One of these balls cannot be covered by finitely many O alphas, because if, let's say, this one would be covered by, let's say, 5 O alpha, and this would be covered by 100 O alpha, and this would become covered by, let's say, 1 million O alpha, then their union would be contained in 1 plus 5 plus 1 million O alphas. In particular, X would be contained in finitely many uh, balls, right? Sorry, finitely many O alphas. Okay, since X cannot be covered by finitely many O alphas, one of these balls, at least one of these balls, maybe more than one, at least one of the balls BXI1 cannot be covered by finitely many O alphas. Okay, let's say uh, okay, B, without loss of generality, say BX11 cannot be covered by finitely many O alphas. Okay, so I have this then. Uh, this ball X11 is never a subset of this X O alpha 1, O alpha 2, O alpha K for any alpha 1 up to alpha K. All right. Now what we do, uh, okay, now let epsilon to be 1 over 2, okay. Since our metric space is pre-compact, every subset is pre-compact. In particular, this subset is pre-compact. Therefore, this thing is covered by finitely many balls of radius 1 over 2. Okay, since X is pre-compact again, its subset is pre-compact, and thus, since it is pre-compact, it must be covered by finitely many balls of radius 1 over 2. Thus, there are finitely many balls of radius epsilon, which is 1 over 2, covering BX11. So let's say this thing is covered let's say by1 1 over 2, by2 1 over 2. How many? I don't know, but let's say k2 1 over 2 for some y1, y2, yk2 in X, right? Because this is pre-compact. Okay, but what I know is this. This ball, okay, this ball cannot be covered by finitely many O alphas. No matter how many you choose, how many of them you choose, they never cover the whole uh, ball. Well, since this is not covered by finitely many such uh, balls, then one of these balls will not be covered by finitely many balls. And here uh, I can of course choose you know uh, these balls so that they all intersect with this ball. So here we may assume that all these balls intersect. Okay, these are not empty. If they are if some of them has empty intersection, I can just throw them out from this union, right? Nothing will change. If this ball doesn't intersect with this ball, I can just throw it out from this collection. Still, the remaining balls will cover X. So there is no harm in assuming that all these balls intersect with this. Okay, and then we do what? Uh, okay, so I repeat the same procedure. Since bx1 1 cannot be covered by finitely many or alphas, one of these balls, okay, at least one of the balls yi 1 or 2 cannot be covered by finitely many or alphas. Say without loss of generality b y1 1 over 2. Okay, so I have what? bx1 1 cannot be covered by finitely many balls. So this way we form we may form a sequence. uh, what kind of sequence? This kind of sequence. I started with x1, and then I know that sequence of balls, let me say sequence of balls bx1 1 b y1 1 over 2, and then there is the third sequence, let's say z1 1 over 4, and so on. What are the properties? So that I will just repeat the same procedure, but this time with epsilon 1 over 4. Okay, so that uh, none of these uh, is covered by finitely many O alphas, and they all intersect. In other words, I have this bx1 1 intersection by1 1 over 2 is not empty. B okay, y1 1 over 2, b z1 1 over 4 is not empty, and so on. Okay. All right. Now let me rename these centers. I have x1, y1, z1, and then maybe w1 and so on. But let me rename these centers. Let us rename uh, the centers as, okay, x1, x2, x3, and so on. Okay, so this is my y1, this is my z1. The next one is the center of the next ball, and so on. So we have what? So we have the following. This balls xi with radius 1 over 2 to the power I minus 1, right? x1 with radius x1 and center radius 1 over 2 to the power 0. X2 is y1, radius is 1 over 2, so when I put 2 for I get 1 over 2 to the power 1, and so on. So this is not covered by finitely many O alpha, finitely many O alphas. And second, what? Dxi 1 over 2 to the power I minus 1 intersection, the next one, I plus 1, right? 2 to the power I is never empty for all I. Okay, this is also for all I. None of these balls are covered by finitely many O alphas, and consecutive two balls always intersect. Well, you see, these balls intersect means what? There is a point in common, right? So if, let's say, W is in this intersection, then we see what? Then the distance between xi and xi plus 1 is less than, of course, the distance xi to w and w to xi plus 1. But this distance is less than, strictly less than 1 over 2 to the power I minus 1. And this is less than 2 to the power I, right? Right? This is in this ball, so this distance is less than this radius, and this distance is less than this radius. And what is this? If you add these two numbers, you get, so this is like 1 over 16 plus 1 over 8. So this is less than 1 over 4, right? 1 over 4. If it were 1 over 8, then it would be 1 over 4, but it is less than 1 over 8. So this is less than 1 over 2 to the power I minus 1. Okay. All right. Well, this means what? The terms of this sequence are getting closer and closer to each other. In particular, we have this. In particular, what is the distance between xn and xm? If n greater than or equal to m, then we have what? Well, again, by the triangle inequality, I have this xn minus 1, xn minus 1, xn minus 2, up to where? Up to the uh, to this term, up to xm. I start with n, I ended up with m. And by this property, I have what? This distance is less than 1 over 2 to the power n minus 1. This is less than 1 over 2 to the power n minus 2. Wait a minute. No, this is less than, yeah. Oh, from the, I have to subtract 1 from the smaller one. Smaller one is n minus 1. So this is n minus 2. I am sorry. N minus 2, n minus 3, up to 1 over 2 to the power. Smaller one is m. So m minus 1. All right. Well, what is this? Okay, which one is the smaller? Uh, this one is the smaller one, so 1 over 2 to the power m minus 1. I have 1 here, and then 1 over 2 up to 1 over 2 to the power this minus this, so n minus m uh, minus 1. Yes. Okay. All right. If I multiply, so m's are gone, minus 2. Yes, so all right. And what else? You see this number here, whatever this thing is, this is 1 plus 1 over 2, 1 over 4, and so on. Whatever this thing is, this is less than 2, right? It never adds up to 2. So this thing is then less than 2 times this gadget, which is 1 over 2 to the power m minus 2. So I assume I obtained this. Hence, the distance between xn and xm is less than 1 over 2 to the power m minus 2, where m is the smaller one if m is less than n. Okay, whichever is the smaller one, I have this. Well, this means this is the Cauchy sequence, right? So uh, claim xn is Cauchy. Why is that? Given epsilon positive, choose m and 0 so that 2 to the power and 0 minus 2 is larger than 1 over epsilon. I can do this because, this is an increasing sequence. This is larger than n 0 minus 2, and natural numbers is unbounded. Therefore, I can choose n0 big enough so that this happens. Now, this implies hence uh, epsilon is larger than 1 over 2 to the power n0 minus 2. So if m and n are both larger than n0, then the distance between xn and xm, well, let me say this way. Okay, I have any two integers. Let's say m is larger than this. I know that this thing is less than, right, here I have if m is larger, right? No, if m is smaller. Okay, smaller one. Here's smaller one. All right, let me choose this way. Okay, 1 over 2 to the power m minus 2, right? M is smaller one. All right. But m is larger than n0, therefore this is less than n0 minus 2, right? The bigger the power, the smaller uh, the number 1 over 2 to the power, that number. And this is less than, of course, epsilon. So we have what? Given epsilon positive, there is some n0, so that if m and n are both larger than this number, then this is less than epsilon. So this shows that this sequence is Cauchy. Hence, the sequence xn is Cauchy. Okay, what if it is Cauchy? Well, we are in a complete metric space, right? We don't forget that. That was our assumption. We assume that XD is complete and pre-compact. I want to show that this is a compact metric space. To prove this, we assumed its negation, and I am trying to obtain a contradiction. And we are very close. This is a Cauchy sequence. Since XD is a complete metric space, this Cauchy sequence, sorry, Xn is convergent to some element, say x0. Okay, so I assume this limit of xn is equal to x0 for some point. All right. Well, you see, I have this x0 here. Okay, this is the uh, limit of xn's. Here I have, let's say, some xn, and this xn is what? There is a ball around this, right? We had this ball. Xn was what? Xn is a ball, so that this Xn is a point, so that this ball cannot be covered by finitely many O alphas. So let me, okay, draw a bigger picture maybe. Here is this x0. Here is, let's say, xn converging to this, and there is this ball of radius 1 over 2 to the power n minus 1, right? It was n minus 1, I guess. Let me check it again. Yes. And this ball cannot be covered by finitely many O alphas. Okay? But we know this. These numbers are, these elements are getting closer and closer to x0, and the radiuses are getting smaller and smaller. And this x0 is in x, therefore it is in one of the open sets O alpha, right? Because O alphas, they cover uh, X, right? This O alphas uh, open cover. This O alphas cover X, but finitely many of them doesn't cover X. Okay. So there is some element since since X is in this cover, all of them covers X, but finitely many of them doesn't cover X. Okay, and X0 is in X. There is some uh, element O alpha 0, so that X0 is in this O alpha 0. All right, so let's see. There is some O alpha 0. Let's say that O alpha 0 is something like this. Okay. All right. Well, since this is an open set and it contains our limit point x0, there is some radius so that the ball with center x0 and radius with that radius lies in this open set. Since uh, okay, so uh, there is some r positive, so that b x0 r lies inside O alpha because O alpha 0 is an open subset. Okay, so there is some ball here. There is some ball here. Okay, there is some ball here. Maybe I'll, okay. Yeah, okay, let me draw it this way. These are open balls, but let me draw it like this and radius r. All right, now I'll do the following. You see, when n gets larger and larger, these points are getting closer and closer to the x0, and radiuses are getting smaller and smaller. Therefore, at some point, this ball will be inside this, blue ball, b x0 r, because both x n is approaching to x0 and the radius is getting uh, to 0. All right, so let me do it this way. I have to choose this n big enough. Okay. All right. So let me say this way. If there is something you don't understand, just stop me and ask, okay? Don't wait. This is one of the maybe most complicated proofs in the book, actually. This is a real, okay, it has several steps, but we are almost done. All right. Now, since limit xn equals x0, there is some n0, so that uh, if n greater than n0, then the distance between xn and x0 is less than let's say r over 2. So I choose some point here, x and 0, so that this distance is less than r over 2. Okay, r over 2. I can do this, and actually all the elements after this index are are in this ball of radius 1 r over 2. All right. What else? I will also choose and 0 uh, big enough. I can always, enlarge n 0, because this holds for all n greater than n 0. So if I increase n 0, nothing will change. But choosing n 0 big enough, uh, we have what? Let me write, so that uh, 1 over 2 to the power n 0. What was the radius of that ball? Yeah, n 0 minus 1 is less than r over 2. Okay, both the distance of this point to x0 is less than this, and the radius is less than this. So I have this. Okay, let me draw again a picture here. So I have this x0, and then I have so this distance is r, and I have a ball with center n0, and the radius of this, whatever the radius, that radius is 1 over 2 to the power n 0 minus 1, and that is less than 1 over 2. And I claim that this is how it looks like. Namely, if I choose a point here, okay, that really lies inside this big ball. So this blue ball lies inside this red ball. Why is that? Well, that's very easy from the triangle inequality. So I claim this. B x and 0 and radius 1 over 2 to the power and 0 minus 1 lies inside b x 0 and radius r. Why is that? Well, to see this, let y is in this, then the distance from y to x0 is less than the distance from y to xn0 plus xn0 to x0. Alright, the distance between xn0 and x0 is less than r over 2, right? If n is larger than n0. So this distance is less than epsilon over 2, but y is in this ball, therefore this distance is less than 1 over 2 to the power and 0 minus 1, but that is also less than r over 2. So these are not epsilon but r over 2. So this is r, and this implies what? This implies y is in the ball with center x0 and radius r. So I started with any point in this ball and I ended up with a point in this ball. So that implies this inequality. This what? Uh, so this ball is contained in this ball. Okay, but that's the end of the world. Why is that? This ball lies inside O alpha. Remember, there is this O alpha here. This O alpha. Okay, O alpha covers this ball. So there is this O alpha here. Alpha 0. Okay, finally, since this ball is inside O alpha 0, we see that which ball? B x and 0, 1 over 2 to the power n 0 minus 1 is contained in one of these balls. Okay, but that's a contradiction. Why is that? Because these balls are chosen so that they cannot lie inside the union of finitely many O alphas, right? Remember this property, that these are chosen so that they cannot be covered by finitely many O alphas. But what I have obtained is this. I obtained that this is contained in just one of them. Okay, therefore in a finite union of O alphas, which is a contradiction. Contradiction to the choice of b x n 1 over 2 to the power n minus 1. Right? These balls are chosen so that they never lie inside finitely many in the union of finite many O alphas. All right. What is the reason of this contradiction? Well, the reason we ended up with this contradiction, we are in trouble now, is the following. We started everything by a lie, right? What was that lie? We assumed that uh, where was it? Okay, we assumed that this is not compact. Okay, we assumed that xt is not compact, and we ended up with a contradiction. Therefore, this assumption is false. Okay, hence xt must be, okay, let me write it. Hence, our assumption that xt is not compact is false. Well, xt is not compact is false. If this statement is false, so xt must be compact. Okay, and this finishes the proof. So this finishes the proof. Okay. All right. Any questions so far? All right. Let me stop the recording.